Hey guys, welcome back. This is Jonathan Gardner. This is section 2 of the logic interlude. And this section, to be honest, this one was really difficult for me to understand exactly what he's trying to say. I think part of the reason is we all think we're logical, but we're really not. That's the first thing you have to admit, is that most of what you think is logic is really justification for the conclusions that you want to draw. So with that in mind, in mathematics, logic is really the element that we're learning. And math is really an exercise of logic. Anytime you use logic, you're doing math. And so this chapter is not so much about logic in general, but logic as it applies to mathematics. And so we're going to cover some of the concepts here. Might take some time. There's some definitions. There's some techniques that he explains. So let's just try to work through it and understand what it is he's trying to say. Okay, now this first paragraph is short, but it's important. Okay. We always try to keep clearly in mind what we assume and what we prove. So we have assumptions and we have proof. And there's a huge difference between these things, right? Okay. The proof is a sequence of statements that you can almost read to a computer. And these proof statements are either assumed or they follow from the preceding statement by a rule of deduction. All right. So these statements, those rules of deduction, by the way, are themselves assumptions, right? So when you say these two statements are connected by this mechanism, you're really assuming that that's such a connection that's valid in logic. So there's a lot of assumptions flying around in logic. The thing about logic is if you don't make any assumptions at all, you don't have anything to do in logic, right? You have to start something with something, and you have to have some kind of rules of deduction that you can use, okay? Now, he starts with this rule of logic. Basically, when you say if A, then B, okay? Statements like this mathematically means that when this is true, then this is true. But if this is false, then this could be true or false, right? What's a good example of this? If it's raining, then I'll bring an umbrella, okay? If it's not raining, I might bring an umbrella anyway. Right? So this statement by itself isn't quite as solid as we often believe it is. There's the converse that says if B, then A. This is the converse of that statement. If I'm bringing an umbrella, then it must be raining. Right? I only bring my umbrella when it's raining. Those two statements are logically more powerful than just the simple statement, if this, then that. You have to say if this, then that, and if that, then this. Then we say A, if and only if B, right? And the same thing. These two statements are exactly the same. There's no difference. Unlike the first two statements, this statement and this statement are different. But these two statements are always the same. Okay, these two statements, they're either true together or they're false together, but they're never different. Okay, and if they are different, then this whole rule is broken. Okay. So in English, you might hear somebody say only if. And this is kind of meaningless in a mathematical context, right? But if you say if and only if, this is more meaningful, right? So try not to say only if by itself. Only say if and only if. So A, if and only if B, okay? And I showed you, I think in an earlier video, you write that as IFF, as a shorthand, because we use it a lot. Okay, what does this mean mathematically? Well, we might see in math something like this. We might see using a red marker and holding the page down with my left hand and bumping the microphone stand that holds the phone that's taking a video. We say if 2x is equal to 5, then x is equal to 5 halves. Those two statements are the same. But also the converse is true. If x equals 5 halves, then 2x equals 5. And so really we can just write this as if and only if 2x equals 5, then x equals 5 halves, or we can say 2x equals 5 if and 2x equals 5 if and only if x is equal to 5 halves. All right, there's another way to say that. Okay, here's an example statement. This will trip you up, this particular one. There's a couple things like this that we already learned. Okay, so we say if, for instance, somebody says, you know, a friend comes down the street and he grabs you and he says, if x equals -3, then x squared equals 9. And indeed, that statement is true. Okay. Now, if you turn to your friend, he says, well, If that's true, if x squared is equal to 9, then x must be minus 3. And this is false, because x could also be 3, right? So this statement is true and this statement is false. So this is one of those examples of the if and only if doesn't hold. It only holds one direction. Okay. Another example. If two lines are parallel, and we'll do geometry soon. Geometry is so much fun. Okay. If two lines are perpendicular, and I won't spell that out, then they have a point in common. Have a point in, I should have used a different color. Okay. If two lines are perpendicular, then they have a point in common. But is the converse true? If two lines have a point in common, two lines have, hooray for handwriting. See, I'm supposed to write like this. I'm used to writing like this, but I'm trying to hold it square for you. Maybe I should move the camera. If two lines have a point in common, but then there wouldn't be much room on the table for my books, then they are perpendicular. I'll use that symbol for perpendicular rather than even writing it out. And this is not true. This statement is not true, because you can have two lines that aren't perpendicular that have a single point in common, right? So just because you see if something then that doesn't mean the converse is true. Okay. All right. Now, you're probably used to proof by deduction. Deduction says we start with some basic statements, we connect them in a meaningful, logical way, and then we get the conclusion and we're like, yes, this is true. Okay, so that's probably the most common technique we use in mathematics to solve our problems. But there's also proof by the method of contradiction. But you have to be careful with this technique. It's not as bulletproof as you would like. Okay, so we want to prove that A, so the statement A is true. Okay, so in order to do that, we have to say either A is true or false. Okay, and some statements don't make sense. There's some statements you can make that are neither true nor false. They're just meaningless statements, or they're both true and false at the same time. Popular example, I think they use this in Star Trek, one of the episodes of the first generation of Star Trek. The example is he approached a robot and he said, "This statement is false," right? That statement can't be false, because if the statement is false, then it must be true since it's not false. But if the statement is true, then the statement is false. And anyway, so it makes no sense. So this statement is false is neither true or false, so it doesn't work for that kind of statement. Okay, so we say either the statement is true or false, and then we say assume A is false. And then you do your deduction, and then you say this is silly. Okay? Therefore, three little dots says therefore A is true, QED, go home, look how smart I am. Okay? And we use this technique to prove that the square root of 2 is not rational. Okay? We use this technique because we said if the square root of 2, okay, so we wanted to prove that square root of 2 is not rational. So we said a number is either rational or not. Okay, either you're in the rational set or you're not in the rational set. Let's assume that the square root of 2 is in the rational set. Then that means you can express it in lowest form as a ratio of two integers that don't have a common factor except 1. And we found out that the top number has to be even, and the bottom number has to be even, and they can't both be even because then they share a common factor, and that's silly. And so we know that the square root of 2 cannot be rational, because trying to say that it is rational contradicts all sorts of things. It's a very popular technique. It's kind of cool to do this, and you feel like a real awesome dude when you do it. Okay, talked about meaningless statements already. Now we're going to talk about something more subtle, and this is something that you need to think about it for a while to understand what it is I'm trying to say in the first place. All right. Okay. So let's say you have this statement 2x is equal to 5. What am I saying? What is this? Is this a logical statement? Is this a rule? Is this a conclusion? Is it an assumption? Right? Well, first of all, we have to say what these numbers are. We know what 2 is. We know what 5 is. We don't know what x is. Is x real? Is it an integer? And oftentimes in the book, you have to know by context, okay? So when you're doing the section on geometry and you see a symbol, it's probably a point or a line, okay? When you're doing the section on real numbers, then if you see a variable, it's probably a real number. And if you're doing the section on irrational numbers, then it's probably an irrational number. Though I think in that section, he's really clear about what is a rational and what is a rational number and what is an integer. Okay? And if this is an integer, then obviously there's no solution to this, so this statement is meaningless because there is no number multiplied by 2. There is no integer multiplied by 2 that equals 5. It doesn't exist. Okay? So you might as well say, gobbledygook. This statement would make no sense. Okay. So he lists out next 1, 2, 3, 4, 5, 6, 7 statements that have something to do with these symbols, 2x equals 5. Number 1, there exists a number x such that 2x is equal to 5. Okay? And he says that first statement is true. There exists a number x such that 2x equals 5. That's true. What if the statement, you're looking at the statement, you say, for all numbers x, we have 2x equals 5. Okay? So in this second one, it's phrased a little differently. We're saying for all numbers x. What do we mean by number? Real numbers? For all real numbers, 2x equals 5? No, that's nonsense. That's not true at all, right? What about there is no number x such that 2x equals 5? Well, if the number, you mean a real number, absolutely there's a real number that you can multiply 2 by to get 5. 5 halves, for instance, okay? So if you're saying there is no number such that 2x equals 5, and you'll see, I'll put down equations saying that this is not true. Okay, I'll say x equals 4 is not true. Okay, I'm not saying x is 4, I'm saying x can't be 4. I'm saying the exact opposite. So in this case, there is such a number that you can multiply by 2 to get 5. So the statement, there is no number x such that 2x equals 5 is obviously false. Okay. D, if x is a real number and 2x equals 5, then x is less than 7. Okay. And for the statement in D, that's true because the solution would be 5 halves, and 5 halves is definitely less than 7. So all that's kosher. What if I said, if x is a real number and 2x equals 5, then x is greater than 7? That's nonsense. That doesn't make any sense, right? Because 5 halves is definitely smaller than 7, not larger than 7. And there's an ordering to the numbers. We can't play games like that. Okay. E, determine all numbers x such that 2x equals 5. And he has a beef with this statement because of the word determine. Okay. He says, in a way, when you have an equation like this, that already tells you the answer. You just have to move the symbols around and you're going to find the answer, right? And so you don't have to do anything. You just have to manipulate the symbols, right? So instead of saying that, you should say something closer to statement F. Express all rational numbers x such that 2x equals 5 in the form m over n, where m and n are integers and n is not equal to 0. That makes a lot of sense. Express, right? So we're taking a statement and we're going to manipulate it so that it says something else. It's a different way to express the same idea. Okay. And finally, he has G. Solve for x in the equation 2x equals 5. Okay. That's a shorthand for saying express the solutions for x. Solve for x. You're going to see solve for x a lot. That's what they mean by solve for x. Okay, so and he has a little note here after statement G. He says, a lot of problems in math arise because you write down 2x equals 5 and you forget what that means. You didn't qualify it, okay? Let's give an example. What does he mean by that? Let's take this nice tan marker, which may be a little brown. We're going to say x squared equals 2. Okay, this is just an equation. If I said there exists a rational number x such that x squared equals 2, then I say that is false. But if I said there exists a real number such that x squared equals 2, that's true. There is a number that you square and you get 2. There's actually 2 of them. Okay. Now this last bit, he starts using some words in very specific ways that mean specific things. So let me pull out the black marker. The first word is equality. Okay, we'll say equals. What does equality mean in context of mathematics? Equality, to me, means that you can use the same two things are equal when both of them refer to the same thing. Okay, so let's say that kind of a weird existential thing. So you have a farm, right? And you have a fence. Okay, and there's a cow over here outside the fence. Moo, okay? And that cow's name is Bessie. What do cows look like? That's a cow? Does that look like a cow? Okay, so Bessie, okay? So I could say, Bessie is outside the fence. And I'm referring to this particular cow, all right? Somebody else could say, hey, there's that black and white cow outside the fence. We're talking about the same thing. Those two things are equal. The black and white cow outside the fence and Bessie are equal. So in many ways, these are just names. 2 is just a name. 3 is just a name. A is just a name. And if I say A is equal to 2 and B is equal to 2, then 2A and B are equal. They mean the same thing. They're just different names for the same thing. So you have to get used to that. On the other hand, we have this thing called equivalent. What does equivalent mean? Equivalent is when two statements are true together or false together. Okay? This is that if and only if stuff, right? So he gives two statements, for instance. He says the number x satisfies the equation 2x plus 5 equals 3, and the number x is equal to minus 1. Those two statements are equivalent. Remember, statements are equivalent. Numbers are equal. Statements are equivalent. They're equivalent because if there is a number x that satisfies 2x plus 5 equals 3, and that number is equal to minus 1, then those two statements are true together. Okay? All right. Equivalent. We do not use the word equality for what we call congruence. We're going to talk about that later. So we have two triangles, one over here, and we have another one over here. Okay? And there's something about them that's the same. Like the lengths are all the same, the angles are all the same, but they're not the same triangles. This triangle's over there, this one's over there, right? So I can't say that A is this triangle and A is also that triangle. I'm going to confuse everybody, right? So we have a special word for this. We call it congruent. These are not equal. And when you get to geometry, don't call congruent shapes equal. It's going to drive you nuts, okay? But you can say that the lengths of the sides of comparable sides are equal. Like the lengths of this side are equal, the lengths of these sides are equal, the lengths of these sides are equal. This angle is equal, these angles are equal, right? The angles and the sides, the lengths are all equal, okay? The lines are not the same. They're congruent, but they're not equal. So these two lines, this line here, are different lines in different parts of the page. They're not equal, but they are the same length. They're equal length, things like that. Okay. So another thing that he kind of nitpicks here, this is the last little section of this book, and I think it is kind of a nitpick, especially as a physicist. One of the problems is that we get this conception that numbers like exist in the real world. Like there's something you can touch and point to and say that's a 2, but it doesn't. There's no such thing as 2 in the real world, in the physical world, right? So when we say 2, right, it's more of a representation or correspondence to something that we see in nature, right? So when we see 2 cows in the pasture, we say 2, that's the number 2, but there's really just 2 cows in the field. This is a description of something that we see. There's a correspondence there. Now mathematicians, what they've done is they've built this wall between reality and logic, and they only care about the logic side, right? Which is cool. You can do all amazing things with logic, and it's a fun game to play. What physicists have done is they still have that wall that separates reality from logic, but the physicists are always looking for ways to represent what's going on in reality with logic. They want a logical explanation for what's going on, okay? So, but that's kind of neither here nor there. That's more of a philosophical discussion. And it is kind of important that you know that these numbers that you're using in math, like 2 or something like that, if they correspond to something in reality, then we have to give it a unit. You know, we have to say 2 miles per hour or 2 kilograms or something like that. So anyway, that's kind of this section. This is a fun section to think about. It's a fun section to talk about. It's really fun to think about what math really is. What is it that we're doing? What is logic really? right? If logic is just a bunch of assumptions and we use them to put together proofs using methods that we assume are true, you know, what is it really we're doing? Are we just like is it just a castle that's meaningless, that's perfectly meaningless? Is logic defined from the assumptions? If we have a different set of assumptions, do we get different logic? Right. Anyway, that's something really fun to think about. I hope you guys enjoyed this video. Take care, and as you can see, math is really interesting. This is where math really gets fun for you. Take care. Bye-bye. Hey guys, thanks for watching this video. This video is part of my series on Sergey Lang's Basic Mathematics. You can click here to watch the rest of the videos in the playlist. You can click here to learn more about me, and you can click here to support my channel. Thank you so much. Bye-bye.